Yeah, I think you forgot it.
Okay, we have I think a short meeting today. We're going to take a look at the effects of disturbances in control systems. And the underlying math or the theory is no different than what we've done before. We're going to use transform work. And remember that we're working with linear systems. So one of the principles that we will use is superposition. All right, so let me sketch a block diagram of a control system which may have disturbances in it. And so here's our process that we're trying to control. And we have a compensator or controller here. We're measuring the behavior at the output. And then we're comparing this output to the reference behavior. If there's an error here, then the controller makes some sort of corrective action. But today what we're going to do is consider that there may be some effect here that's undesirable. R is the reference or the desired behavior. Disturbances are generally undesirable, and this is the output. Okay, so this is the problem that we're going to consider today. What is the effect of the disturbance on the output? We're using Laplace transforms for modeling, so let's give this controller a transfer function C of S, and we'll give the process a transfer function G of S. Okay. So the control system, if it's operating well, the output would follow the desired behavior, the reference. The error would be small, but now we have somebody working against us as well. All right. You may want to say, hey, maybe if he's working against us, maybe that should be a minus sign. But that's not so important today. The important thing today is to remember that we could analyze this problem by using superposition. So the next thing we're going to do is let's describe what is the model of the output. What is the output in terms of the two inputs? So this is a system with two inputs. The two inputs are R and D. R is the reference behavior, D is the disturbance behavior. And so we could write a model for this block diagram. Let's write the model of the output in terms of R and D. So let's say Y of S. There's some transfer function between R and D, so I'm going to write that like this. I'm going to leave this right here and say R is like this. But the output Y is also affected by the disturbance. And so we could use superposition and figure out another transfer function between the disturbance and the output. So this is very much like circuit analysis in the sense that when we have multiple sources, multiple current sources, voltage sources, we can kill one term, kill one source, and analyze the effect of the other source. And then we kill the first source and then analyze the effect in the second. So this is a concept that goes all the way back to circuit analysis. The only thing we're adding today is a different notation, a notation that is used for system analysis. So we're learning to basically exercise these functions here. So let's take a look at this block diagram, and let's write here now the transfer function from this input, R, to the output Y. So going from there to here. We know that this formula in the top, we should have the forward gain from R to Y. So we take the forward gain here, and using these notations here, we have C times G. Any questions, concerns? And in the bottom, we remember the formula for a single loop is 1 minus the loop gain. The loop gain, not the loop function, the loop gain in this case is going to be everything in the loop, including all the different signs, SIGNs, that we have to be concerned about. And so here we have a minus C times G. So I have 1 minus the loop gain. 1 minus the loop gain. The loop gain is C times G of S with a minus sign, which turns this into a plus sign. All right? A very familiar looking transfer function to us. Now let's take a look at the transfer function from the other input. So let's ignore now the effect of R. Take it out, make it 0. And now let's take a look at the effect of this input to that output. So again, the forward gain, let's take a look at the forward gain from D to Y is G of S. And then we have to say 1 minus the loop gain. And again, the loop is unchanged, and so we have plus C G of S. So we got to this point basically by using the principle of superposition. Okay, we have two inputs, so we just treat them separately. Any questions at this point? All right, now let's take a look and see what these two functions tell us. So this thing, you see it in both terms in the denominator. Recall, we call this the loop function. Okay, loop function, very similar to loop gain. It's very similar to loop gain, but we ignore the minus sign. Now let's take a look and see what happens when CG becomes large. Let's see what happens when the loop function increases. When CG becomes large, Y over R, what does that become? In the limit, if C times G gets large, what does this function become? It becomes close to 1, right? So Y over R becomes, in other words, CG over 1 plus CG, it becomes 1. The implication is that the output follows the reference. Okay. So this is one observation. But let's take a look at the other function, this transfer function. This transfer function is the relationship between D and Y. And so Y, the effect of D on Y, let's see what is that. That is G over 1 plus CG. As this term becomes large, what does this tend toward? It tends to get smaller. Okay. So this is one effect. We see that the output tends to follow the reference, but with the other function, what we notice is that the effect of disturbance is reduced. So this is one of the principles of feedback. Okay, this is one of the conclusions that we can make about feedback systems. A large loop function, people will usually call it gain. Large gain can reduce the effects of disturbances. Okay? Large loop gain can reduce the effects of disturbances. Okay, this is why we use feedback. One of the reasons we use feedback. There is a caveat, of course. What is the caveat? Okay. Your mom and dad want you to grow up to be a productive citizen. So what do? They certainly observe your behavior, and using that feedback information, they parent you. Okay? How many of you had strict parents growing up? A few of you. Okay? You turned out pretty well. Maybe, right? Because we also know that sometimes the effect of very strict parenting can sometimes, in some cases, produce undesirable effects. Some personalities don't respond well to large, high gain, okay? We call that helicopter parents. So what is the caveat about large loop gain? Could destabilize, okay? So more is not always better. So if we're faced with the need to retune the system, we need to be careful. We need to realize there's a certain benefit sometimes to using increased gain, but we may destabilize the system. Okay, let's take a look and apply the same idea now, and let's take a look at the effects of measurement noise. So I'm going to draw the same block diagram again, but I'm going to add another signal. So in general, when we sample the output, when we measure the output, almost always there's going to be some measurement noise. Okay. There's always measurement noise. There can be inaccuracies in the information that you get. We experienced this, for example, when we're over in the computer lab about a week ago. Somebody said, "Man, the air conditioning is really loud, Dr. Hong, I can't hear you." Okay, so you're trying to hear what's coming out of my mouth, but the air conditioning noise corrupts the information, and so it can affect what's happening. So, how do we analyze this system? Now we have a system with 3 inputs. 1, 2, 3. Problem's a little bit more complicated. How do we simplify it? We apply superposition. Again, we can simplify problems a little bit. Let's consider taking this out, and now just look at the transfer function between y of s over n of s. The transfer function from noise to the output. What is the effect of noise on the output? Okay, so same principle. Forward gain take the forward gain from n to y, and I get minus Cg of S over 1 minus the loop gain. The loop gain again is Cg, and the minus sign here, like so. So what would be our conclusion here? As loop gain increases, okay, so this minus sign simply means that if the noise increases, if the noise signal increases a little bit, my output is going to respond by going in the opposite direction. But the magnitude is still 1. Magnitude is 1. And of course, we could also easily change the sign from minus to plus if this had been a minus sign. So our conclusion here is that feedback doesn't reduce the effect of all disturbances. Here's a disturbance, D. Here's another disturbance, D. But when we were studying this disturbance, this was a plus here, we got the effect that large loop function can reduce the effects of disturbances. Let's go back and take a look at that function. That was this function, G over 1 plus Cg. As this increases, this thing tends towards 0. But here, the disturbance comes in the system in a different place. Okay. So we had to be a little bit careful about our conclusion. Not all disturbances have their effects reduced by using large gain. Okay, so in summary, this is what we did. We studied today the effects of disturbance in control systems. We basically used the principle of superposition. We wrote their functions down. We wrote down the models, for example, and we just studied the effects as our loop gains increased. Any discussion? Questions? Okay, I said today would be kind of a short meeting, and this is where I end today. I can stick around if you have any questions.